All right, next I'd like to look at some application problems that tie together a couple of things that we've learned. In particular, in the next couple of examples, I'd like to combine the centripetal force relationship, which you're all, I think, very familiar with from the midterm, and conservation of energy into a single problem. And so we've seen this kind of thing before. We look up at the data projector. We could have a car that, let's say, is moving along and then wants to go all the way over the top of a hill without losing contact with the track, and then back down again. And so the question that I'd like to ask is actually a similar one to the following, in which we've got a mass. It could be like a little kid's sister being swung on a swing, something like that. And we could ask, what's the initial velocity need to be at the bottom so that she just makes it up over the top? And that would be mathematically the same problem. So you give her a little push, give her a little push like that, give her a little push like this, and then you go, can't you do any better than that? And I go, okay, you little sweetie, all the way up over the top. Okay. And so let's find what that velocity is at the bottom so that the object just makes it over the top. In this case, we'll make it a car. It'll work equally well for a mass on a string. Okay, so let's find V naught at the bottom so that the car, in this case, just makes it over the top. Without the wheels losing contact with the track. And for this problem, since this is a pretty big track, we'll make r here equal to, let's make it 10 meters. Okay, so what we can do first of all is set up our kinetic energy expression. So we use conservation of energy, and we can say that 1/2 mv naught squared plus mg y naught is going to be our kinetic plus our potential at the bottom. Here at the bottom, we'll call this y initial equals 0, and at the top, in energy, we don't care, remember, what the path is it's taken, but just the vertical change in elevation. So here y final will be 2r. Not pi r, as would be the case if you followed this path along the arc, the circular arc path, but just the vertical distance that you are above the ground. And so that'll be our y final is 2r. So you have 1/2 mv naught squared plus mg y naught equals 1/2 mv final squared plus mg y final. And so I wonder, well, why do we even need this centripetal force equation? Looks like we can just solve it. This is going to be easy. This is just like a mass on a string, really, because this problem is the same. You've got a radius, and the only thing that's different is that instead of a normal force, you have a tension force. That it's exactly the same problem mathematically. If you just replace the normal force of the track with the tension force, then you could say here, without the cord going slack, instead of without the wheels leaving the ground. So you say, okay, well that's great then. I just give it enough speed so that it just makes it up over the top, and so the final velocity here is 0. That's what a lot of people do. But the problem with that is if the final velocity here is 0, whap, just falls straight back down. The wheels lose contact with the track. So this is why we need a constraint on V final so that the centripetal force will equal mv squared over r. so that you will be able to maintain contact with the track and the wheels. Okay, and so we need a separate calculation for that. And that calculation will involve the centripetal force at the top of the path. So let's just draw that in here as a separate problem. Here are wheels, here's our person, and then here's going to be the normal force. And remember, the normal force is always perpendicular to the surface. So in this case, that's in the same direction as mg. If you're at the bottom, it wouldn't be, but at the top, it is. Okay, and so you can say that the sum of the forces inward, F normal plus mg, equals mv squared over r. But if we want the minimum velocity, we get the minimum velocity when the force normal just equals 0. This is the velocity at the top, not at the bottom. V min at the top happens when F normal equals 0. Okay, so if F normal equals 0 at the top, then why doesn't it leave before it gets to the top? Well, if we think, instead of F normal, let's think of it with a tension. The tension here has to be more than the tension here, okay? Because it's moving faster at this point, because the kinetic energy is decreasing, right? So that means the tension has to be bigger here than it is there. And also, the component of gravity that is acting toward the center is smaller here. Here it's all of the gravity is acting toward the center. Here, only part of the gravity is acting toward the center. So it's moving faster, which means more tension. And you're getting less help from gravity, which means more tension. But by the time you get to here, then you're at the minimum tension, which is 0, or the minimum normal force. Then you get over to this side, then it starts to speed up again, and now the gravity force is not totally pointed toward the center. So that's not helping the tension force produce the centripetal force, so the tension force starts going back up again. So it's non-zero, it can be 0 right here, but only there, and then non-zero again when it gets back over to this side. And so that's why it can be 0 at the top and not be 0 anywhere else. So to get V min, we'll just cancel out that normal force from this equation. We'll set it equal to 0, and we'll solve for V. So it's V at the top. That's the minimum velocity at the top then. It's going to, the masses will cancel, so it'll equal the square root of Rg. So that now becomes the V final in this kinetic energy expression, if we're looking for the minimum velocity at the bottom. Okay, so it's actually 2 equations that we need, and you don't want to just go through. And I've seen this so many times before. So I'm just warning you, don't do this, because I've seen a third of the class do this before on exams. They just go through, they write this equation, and they go, the V final is 0 at the top, cancel out that term. They don't ever use the centripetal force relationship. And so that's a major error. And it's something that people do all the time. So make sure you understand why that's not right. Okay? And so what we can do here then is just rewrite the energy equation, 1/2 mv naught squared, plus 0, because there's no potential energy at the bottom. The bottom here is our 0 reference position, equals the final 1/2 m times square root of Rg squared, okay, because that's V final at the top, so that the normal force just goes to 0 there, but nowhere else, plus mg times 2r. That's our y final. Okay? And so now we can go through and simplify a little bit. Because there's no springs in this problem, the energy equation with just kinetic and potential, the masses will cancel. So it doesn't depend on the mass. Okay, so we have 1/2 V naught squared equals 1/2 times Rg, right? Because that's the square root of Rg squared, plus 2 Rg multiply through by 2, you get V naught squared equals RG plus 4RG, or 5RG. So that gives you V naught equals root 5RG. So that's kind of a standard result for the minimum velocity at the bottom, so that it just makes it over the top. This is without friction. Now, if you have friction in the problem, that creates some difficulties. And so that's why usually we don't do it with friction. Because at every point, at every angle, you've got a different normal force, which means you've got a different friction force at every point. If this thing is sliding, if it's rolling, then you'd have to figure it out in terms of rolling friction. And so reality gets so complicated, it just makes my head hurt. And so I'm not even going to try to deal with that one. And so here, let's try this then with r equals 10. This VV naught is the square root of 5 times 10 meters times 10 meters per second squared. And so that's going to be square root of 5 times 10. Which is 22.3 meters per second. So that would be about 44 miles an hour with a 10-meter radius track. So it just makes it over the top. Now, would you feel safe if you're at that minimum velocity in a real-life problem? Probably not, because in a real-life problem, we all know that there is friction. So that means that that velocity is not good enough with friction in the problem. And so I want to make sure that I have a little bit of extra velocity to make up for any losses that might have happened in that more complicated friction problem. All right, so that's the first example I wanted to look at. In the second one, and notice here that what we did is we just took the energy equation and the centripetal force equation, we combined them, okay? That's what we did. We took the centripetal force equation, the energy equation, we put them together. And so I'm going to do that again in this next example. This next example, let's say we have a woman skiing down a hemispherical hill with no friction. And let's say that the radius of the hemispherical hill is 10 meters. Starts from the top, and has an initial velocity of 0 at the top. And as she starts to move with mu k equals 0, let's find the height above the ground where she leaves the circular hemisphere. So this is a circular path on a hemisphere. Circular hemisphere may sound a little redundant, but that's why I wrote it. Okay, so here we are at this point. And so when she reaches this point, she's getting a little more worried because she's getting ready to leave the track. So I'm hoping that down here there's another ski jump that she can pick up and she's not just going to crash and burn. But at this point, she's going to reach some critical point where, and this is the way I'm thinking about it now, when does the normal force go to 0? So in other words, when does the surface not have to push up any longer to prevent her from supporting the weight so that she doesn't fall into the hemisphere? And so what I'm going to do here is I'm going to draw the forces acting on her at this point. So this is for the centripetal force part of the problem. So here we've got F normal. Here we've got mg. But in the direction of F normal, which is toward the center of spin, let me just do that on a little side thing here so we can make this a little bigger. Here's the normal force. Here's mg. Now if this angle here is theta, then that angle there is theta because opposite interior angles are equal. And so I find it convenient to measure the angle in this problem from the vertical, but you could do it from the horizontal too. Then the cosines would just turn into sines. And so the component of the weight which contributes to the centripetal force is this part here, which is mg cosine theta. And then this part is the part that accelerates her down the incline. That's the mg sine theta. Okay, so we have a difference then between mg cosine theta and the normal force. Remember, you define the positive direction toward the center of spin. Okay, now you can get away with that sometimes, and I saw some of you on the midterm did that. But it's not the best way to handle the problem because the positive centripetal force is in the direction that we should define as positive, so we don't have to put negatives on our acceleration, which can confuse us. Okay, so here we can say that the sum of the inward forces toward the center of spin at this point where she leaves the surface is equal to mv squared over r. And so in general then, before the normal force has gone to 0, make the normal force smaller, we've got mg cosine theta minus fn equals mv squared over r. Because the normal force points away from the center, mg cosine theta is what's supplying the centripetal force. That's pointed toward the center. And so at theta equals theta max, we have F normal just goes to 0. So at that point, you can set mg cosine theta equal to mv squared over r. That gives you v is equal to square root of rg cosine theta. Okay, so that then is our v final. So this is the initial point, this is the final point. Now we can write our conservation of energy equation. Now, I have told you in the past to choose the bottom point in the path as your zero reference position for potential energy. However, in this case, that's what we're solving for. That's our unknown. So you don't know where to put that yet. And so I'm going to put it on the ground because that's also in reference to what's asked for in the problem is the height above the ground when she. So if I set this up in terms of the ground being y equals 0, then y initial here is r, because it's 1r above the ground, and then h is going to be r cosine theta. So I can write everything then in terms of r and cosine theta. And so this is my y final. Okay, so I've got my v final here. That's the final velocity at this final point at the critical value when F normal equals 0. Okay? And so now I can write the energy equation, which is just the same old energy equation that I've been writing before. 1/2 m v naught squared plus mg y naught equals 1/2 m v final squared plus mg y final. Okay, now the initial velocity is 0, so that's gone. So we have mg times r, because y naught is r. And then v final is this. So we've got 1/2 m times square root rg cosine theta squared. That's our final, plus mg times, and then y final, we want to also, we don't want it in terms of h, but in terms of r and theta, because that's what everything else is in terms of. So I'll write this as mg times r cos theta. Okay, so this is the equation that we need to solve. And so if we work this thing through, what we get is mgr equals 1/2 mgr cosine theta plus mgr cosine theta. And so that's just taking all of that and plugging it in. And so everything now is in terms of mgr and cosine theta, but look at what's happening here. The whole mgr thing is going to cancel. So we get mgr equals 3/2 mgr cosine theta. And I could have canceled out the mgr in the previous step, but I'm waiting to do that here. So the m's cancel, the g's cancel, the r's cancel. Okay, so is this 0? No, this is 1. We canceled out. That means we're dividing through by it. It means we're left with 1 equals 3/2 cosine theta. So that gives us cosine of theta is 2/3. So that's my solution, my simultaneous solution to the energy equation and the centripetal force equation. Remember that in the centripetal force equation, we needed the component of the weight that acted toward the center, subtracted off the normal force, but then at the critical point, the normal force was 0. So that gave us V final. And then we just used the energy expression where we wrote y final here as h, which is r cosine theta. So we're left then with a condition on theta. Can we use that to get the height? Well, yeah, because we know what r is, and we know what cosine theta is. So do we really need to solve for the angle? The answer is no. We don't need the angle. Nobody asked for the angle on this problem. Just asked for the height above the ground. So the height above the ground is r cosine theta. This thing is screaming, solve me for an angle, isn't it? It's saying, I want an angle. But no, you don't even need it. It's okay. You could find the angle, but then you just have to take the cosine of that angle to get the height. So you might as well just leave it as cosine theta. So that, I'm not curious. I don't care what that angle is because it wasn't asked for in the problem. So this is just r times 2/3. So that's 6.66 meters above the ground, or 2/3 of the way to the top.